In this video, I'll go over the activity done in our first discussion session. The activity is called Whose Carbon Footprint is Bigger? On this slide, you can see the problem that you were asked to solve. You have information about both students' transportation choices in a bulleted list on the activity, which isn't included on this slide. And the question is, based on transportation only, which student emits more CO2 molecules to the atmosphere each year? So to answer this question, you want to compare all transportation emissions of student A with all transportation emissions of student B. And this is a review activity. So a lot of the things you're going to do for review here are use dimensional analysis in your calculations, carry significant figures through calculations. Other review material covered is the use of units and unit conversion, and also the use of molar mass and Avogadro's number. So first, laying out the problem-solving strategy, you're trying to compare student A with student B. And each student has two different modes of transportation that they're using. So student A rides a bus to and from school each day, and also flies on a plane to visit her family twice a year. So you're going to have two different calculations here, one for the bus and one for the train. And for both of those, if we go back to the question at the top of this slide, what we're trying to find is the number of CO2 molecules emitted by this bus transportation of student A each year. And then you're doing the same thing, finding the number of CO2 molecules emitted per year when this student uses a plane to visit her family. And then student B is using two additional types of transportation. Student B drives to and from school in an electric vehicle and also takes a train to visit family each month when school is in session. So what you've really got is four separate calculations: the calculation for the bus, calculation for the plane, calculation for the EV, and calculation for the train. So once you have all of those, you can do some comparisons. So you're going to basically add up the bus plus the plane will be the total for student A. And then you'll have the EV plus the train, which will be the total for student B. So let's start these calculations. I'll start on the next slide with the first calculation. So this will be for student A, and this will be for the bus. So you're given in this problem that the distance to student A's school is 12 kilometers away. And each day, this student goes to and from school. So 12 kilometers each way. So you need to multiply the 12 kilometers by 2. So each day, the student is traveling a total of 24 kilometers by bus. So what you ultimately want to know is the number of molecules emitted each day when the student travels 24 kilometers by bus. Other information that you're given is that the gas mileage for the bus is 3 miles per gallon of the natural gas that is used to power the bus. You also know that for every 1 mole let me write this the other way around. You also know that for every 16.04 grams of methane that is burned, so the methane, the CH4, is the natural gas, you have 1 mole of methane. That's the molar mass. This is some review from your prior knowledge coming into Chem 161. You determine that from the periodic table, so you should know how to make that determination using the periodic table. And then the other piece of information you're given is that for each mole of methane that's burned to power the bus, 1 mole of CO2 is emitted into the air. So these are the 3 conversion factors that you're given in this problem that you're going to want to use in the calculation. Another useful conversion factor is going to be density of natural gas. So the density of natural gas is 6.073 pounds of natural gas per every gallon of natural gas. So this is density. This is another review concept. Whenever you want to convert from a mass to a volume or a volume to a mass, you can use density. And you're going to want to do that in this case because it's like solving a puzzle. You know you're starting with 24 kilometers. So let's start doing some calculations here. The student travels 24 kilometers every day. You know that for every 3 miles that are traveled, you're going to be using 1 gallon of natural gas. So miles is a distance, kilometers is a distance. So you can use that conversion factor if you convert kilometers to miles. So you can look this up on your own, that there are 1.60934 kilometers per 1 mile. When you look up conversion factors like this on the internet, just using something like Google or a search engine that's similar, if it's the same type of measurement, such as a distance, in this case miles in distance, kilometers in distance, you can find reliable information on the internet. When you're looking up other chemistry things on the internet, just be careful because all the information out there on the internet about chemistry is not very reliable. But when you're dealing with the same type of measurement, such as distance or weight, we're going to convert grams to pounds in a minute here as well, those are reliable. So kilometers will cancel. Now I'm setting up my dimensional analysis by canceling numerator and denominator. Now we can use this conversion factor that we're given. So for every 3 miles that are traveled, we're using 1 gallon of gas. So now miles will cancel and you've got gallons. What you can do now is use density and say that in every 1 gallon of gas, you have 6.073 pounds of that natural gas. So gallons will cancel. Next, you can convert pounds to grams. So you want to do that because if you go up here to this other piece of information you're given with molar mass, you've got the mass of methane in grams. So if you can convert pounds to grams, then you can use the molar mass to convert grams to moles. So this is another conversion factor because they're both units of mass that you can just look up using a search engine on the internet. So if you look this up, you'll find that there are 553.592 grams of methane per pound. And next, you can now use your molar mass. So pounds cancel, you now have grams. I'm going to continue on the next line here because I'm running out of space. You can use the molar mass and say 16.04 grams of methane gives you 1 mole of methane. So now grams of methane are canceling out. The next conversion factor you use is the one right below the molar mass. This is a 1-to-1 ratio, so it's not going to affect the actual numerical answer, but I'm going to write it here just to show kind of best practices for when you're doing dimensional analysis, where you always want things to cancel as you're moving along, and also just to be clear about how I'm getting these answers. So moles of methane will cancel. And then the final thing you need to do is one more review concept that's part of this activity. And that is getting from moles of a substance to molecules of a substance. And the way you do that is to use Avogadro's number. So Avogadro's number says that there are 6.022 times 10 to the 23 particles, or any things, per 1 mole of that thing. So we're dealing with CO2 here. So what you can say is you have 6.022 times 10 to the 23rd molecules of CO2 per 1 mole of CO2. So moles will cancel out, and you're finally left with molecules. So what you'll get is 5.141 times 10 to the 26th molecules. The final thing you want to do here is multiply this by 180. The other piece of information you're given is that there are 180 days of school per year. So if you're trying to find the amount of CO2 molecules emitted in a year, and there are 180 days of school per year, you have to multiply that amount of molecules emitted in 1 day, which is what this 5.141 times 10 to the 26 molecules is, by 180 days to get the total amount of CO2 molecules emitted in 1 year. So when you do that multiplication, you get 9.2538 times 10 to the 28 molecules. So before we move on to the next calculation, I want to make a note of the number of significant figures you're dealing with here. So you have 24 kilometers being one of the numbers that's given. That has 2 significant figures. 3 miles per gallon. That has 1 significant figure. And that's the number with the least significant figures. So your answer is also limited to 1 significant figure. So I like to use brackets to indicate, because what you want to do is not round yet. This was for the bus. You're also going to find out what student A emits when she uses the plane to go visit her family. So you want to keep the numbers expanded. You don't want to round them before you do your final calculations. If you round too early, you can get something called rounding error, which means that your final answer could be inaccurate, not because you did anything in the calculation wrong, but simply because you rounded too early. So make sure you leave the numbers expanded. So here's our final answer for student A for the bus. And we're going to come back to this number in a little bit and add it together to what student A uses for the plane. So let's do the plane calculation. So this is still for student A. Now we're dealing with the number of CO2 molecules emitted per year by student A from the plane. So student A only takes the plane, goes to visit her family twice per year on the plane. Information that you're given here is that student A flies 808 miles from Seattle to San Francisco, California, to visit her family. And she does that twice per year. So it's 808 miles one way. So you have to multiply that by 2 to get the total miles for one trip. And then she also does this twice per year. So you multiply by 2 again to account for the 2 trips. When you do the math, you get 3,232 miles. So that's a starting point for your calculation. I'm going to start with the 3,232 miles, and I'm going to use the gas mileage of the plane, which you're given as 50 miles per gallon. Miles cancel. Now you know the number of gallons. This is a similar process to what you did for the bus, except you're using slightly different numbers. Another piece of information you're given for the plane is that burning the jet fuel in the plane emits 10 kilograms of CO2 per gallon of jet fuel burned. The other information you have is the molar mass of CO2. So you're given that 44.01 grams of CO2 give you 1 mole of CO2. So if you want to be able to use that molar mass as a conversion factor, you need to convert kilograms to grams. So in 1 kilogram, you have 1,000 grams, and now you can use this molar mass, 44.01 grams of CO2 in 1 mole of CO2. And now we're almost to molecules. Everything's canceled here, right? Grams of CO2 cancel, kilograms of CO2 cancel, gallons of jet fuel cancel. Now you're in moles. And once you're in moles, you can use Avogadro's number to get you to molecules. So the last step in this dimensional analysis is that for every 1 mole of CO2, you have 6.022 times 10 to the 23rd molecules of CO2. So when you do that, the moles will cancel, and you're left with 8.8449 times 10 to the 27 molecules. So this is the final answer for student A for the plane. So the last thing you need to do now is add these two numbers together. If we go back and look at how many CO2 molecules are emitted when the student travels by bus, we're going to move this 9.2538 times 10 to the 28 molecules number over to this page, or this slide. So we've got 9.2538 times 10 to the 28. That's from the bus, and we know that this number had one significant figure. We want to add that to the number we just calculated for the plane. And we also want to think about how many significant figures this number has, because when you add numbers together, the rules for carrying significant figures through calculations are a little bit different. So if we look at all of the numbers we used in this calculation, we also only have one significant figure for this value, because the 50 miles per gallon, 5 is the only significant figure. For the 10 kilograms of CO2 per gallon of jet fuel, you also have only one significant figure. So for both of these numbers, you have only one significant figure. So when you're dealing with significant figures in addition and subtraction, you have to look at the placeholder, or the place of the number you're dealing with. So what I'm going to do is I'm going to put these numbers in the same scientific notation in terms of, I want them both to say 10 to the 27. The first number says 10 to the 28 right now, so I'm just going to adjust this number so it says 92.538 times 10 to the 27. So now we can compare the numbers a little more easily. So this first number has precision to this place. The second number has precision to only this place. So if you look at where that place is located in this number, it's right there. So the second number has more precision than the first. And when you add these two numbers together, you'll get 1.0138 times 10 to the 29 molecules. And I'm going to do the same thing that I did for that first number. I want them in 10 to the 27 units so we can do a little bit easier of a comparison here. So I'm just going to rewrite this. It's the same number, just a different exponent for the scientific notation. And what you can see is that this is the place that we're going to need to round to, right? Because that's not correct. You have the most precision. You have the least precision right here. So this is the place we're going to need to round to. You need to round to the place for the number that has the least precision. This number has less precision than this number. So you're going to round to this place. And when you do that, you get 1.0 times 10 to the 29 molecules of CO2. So that's the final answer for student A. I'm going to keep this answer in mind. We'll come back and look at it after we do all of the calculations for student B. So student B uses an EV. So let's do the calculations for the electric vehicle first. What you're told about student A is that student B is that this student is 5 kilometers away from school, and you have to multiply that by 2 because the student goes there and back every day. So I'm going to use that 10 kilometers as my starting point, and for this calculation you're still trying to find molecules, but it's going to be a little bit different than the other two so far because we're dealing also with power generation in a coal-fired power plant, which is where the electricity used to charge the EV comes from. So some information that you're given is that you have 30 kilowatt hours of charge in that electric vehicle per 100 miles. So to go 100 miles, the electric vehicle requires 30 kilowatt hours of charge. The other piece of information you're given is that each ton of coal produces 2,500 kilowatt hours. So for 1 ton of coal burned, you get 2,500 kilowatt hours of electricity produced. And then you're also given information about CO2 emissions from 1 ton of coal. You get 211 pounds of CO2 emitted for every 1 ton of coal that's burned. So this is information you know. You've got these 3 conversion factors. You're also going to use the molar mass for CO2 again, which is 44.01 grams of CO2 per 1 mole of CO2. So you need to use that molar mass again, and you're also going to use Avogadro's number again. So let's move forward with this. We're going to start, I'll move this down because now we've run out of space. We're going to start with that 10 kilometers. And we can use this conversion factor between the mileage of the EV and the kilowatt hours if we can convert kilometers to miles. So I'm going to do that. There are 1.60934 kilometers in 1 mile. We use the same conversion factor for the bus for student A. And now we can go up and use this conversion factor. For every 100 miles that electric vehicle travels, you need to use 30 kilowatt hours of charge. So now miles is canceling, kilometers is canceling. Next, you want to relate kilowatt hours to the amount of coal used, which you can do using this conversion factor. So you get 2,500 kilowatt hours of electricity for every 1 ton of coal that's burned. So now we get rid of the kilowatt hours. We're getting closer because we have a mass of coal. To get from a mass of coal to an actual mass of carbon dioxide, we can use this conversion factor. So you say for 1 ton of coal burned, you get 211 pounds of carbon dioxide emitted. So now tons of coal cancels. I'm going to move to the next line because I'm running out of room. You can now again convert from pounds to grams, because once you do that, you can use the molar mass here to get you to moles, and then Avogadro's number to get you to molecules. So I'm going to use that same conversion factor we used for the bus for student A, which is 453.592 grams in 1 pound. So pounds will cancel, you're left with grams. Now you use the molar mass, 44.01 grams of CO2 in 1 mole of CO2, and then finally Avogadro's number. In 1 mole of CO2, you have 6.022 times 10 to the 23rd molecules of CO2. So moles of CO2 will cancel, and then the answer you get is 9.765 times 10 to the 23 molecules. You have to multiply that by 180 days, because just like with the bus for student A, student B is using the electric vehicle to get to and from school for 180 days. So when you do the math there, you get 1.758 times 10 to the 26th molecules of CO2 emitted by the traveling that this student does by electric vehicle every year. So this is the first answer for student B. It's got one significant figure because of the 30 kilowatt hours number and also the 10 kilometers. Both of those numbers have only one significant figure. So we have to do the final calculation for student B, which is going to be travel by train. So what you're still told for student B is that student B takes a train to visit family each month that school is in session. And you know that school is in session for 9 months. So I'm just going to figure out the number of CO2 molecules emitted for 1 month, for one trip, and then I'll multiply that by 9 at the end. So one thing you know is that this student travels 1,687 miles from Seattle to Milwaukee by train. That's one way, so you need to multiply by 2 to get a there and back, which is 3,374 miles. So you take this number as your starting point, and this calculation is going to be fairly similar to the one for the bus for student A, because you have mileage in terms of the burning of diesel fuel. It takes 7.97 liters of diesel fuel to travel 1 kilometer. So you've got a distance there with kilometers. So if you can convert the miles to kilometers, you can convert now a distance to the amount of fuel used. So I'm going to use that same conversion, 1.60934 kilometers in 1 mile. Miles cancel, and now I can use this conversion where I have 1 kilometer of travel for every 7.97 liters of diesel fuel used. The next step is to use another number you're given. So you're told also that diesel fuel emits 10.2 kilograms of CO2 for every gallon of fuel burned. So before you can use this conversion factor, you have to convert liters to gallons. And once you do that, you can use gallons. So I'm going to convert liters to gallons. This is something you can look up because they're both units of volume. This is reliably found with an internet search, and it will be accurate. So 3.78541 liters in 1 gallon. So you can cancel now the liter units and you have gallons, and now you can use this number which is a density. Whenever you go from volume to mass or mass to volume, you're going to use density, an important review concept here. So 10.2 kilograms of CO2 are emitted for every gallon of diesel fuel burned by this train. So now you have kilograms of CO2. I'm going to continue the calculation on the next line. The next thing you want to do is go from mass to moles and then moles to molecules. So in order to use molar mass, which is in units of grams, you have to convert kilograms to grams. And now I can use the molar mass, which is 44.01 grams of CO2 for every 1 mole of CO2. So grams will cancel, kilograms have canceled. You have moles of CO2, and then your last step is to use Avogadro's number and say in every 1 mole, I have 6.022 times 10 to the 23rd molecules. Now moles will cancel. And looking at my answer key, it appears I made a mistake here because I did not multiply by Avogadro's number in my key. So I'm going to do a quick calculation here in real time. 3374 times 1.60934 times 7.97 times 10.2 times 1,000 times 6.022 times 10 to the 23rd. I'm going to take that and divide it by 3.78541 times 44.01. All right, thanks for your patience there. I usually try to do all the calculator work beforehand to save time. So the final answer here is 1.5956 times 10 to the 30th molecules of CO2. And for this one, you actually have more than one significant figure. So the miles have 4 significant figures. The liters have 3. Kilograms of CO2 have 3. And your molar mass has 4. So you're actually going to have 3 significant figures here. So we've got that number. We're going to bring the number for the EV into the picture and add these two together. So the student emits 1.758 times 10 to the 26th molecules of CO2 driving the EV. Oh, hold on. Let me back up. Before we do that, I also forgot to multiply by 9 because the student makes 9 trips per year. So let me quickly multiply that number by 9 and I get 1.4361 times 10 to the 31 molecules. So I'm adding that number to the number for the EV, which is 1.758 times 10 to the 26, right? This is what we got here. And we have one significant figure there. 3 significant figures here. So just like with the other case, I am going to make the comparison between the digits of significance and see which number is more precise. So in order to do that, I'm going to move the decimal place for this number. So to get to the 26th, I have to go move it here. It'd be 10 to the 30, 29, 28, 27, and then one more is 26. So I'll have 143,610, kind of, oops, putting the decimal there, times 10 to the 26th. So now we can make a better comparison between these two numbers because we've got the same exponent. You've still got these three being significant figures. So this number has more precision. So it's the more precise one, but when you're adding numbers together, you have to limit your precision to the number that has the least precision, which would be in this place. This place here is not even represented, right? It's 1, 2, 3, 4 zeros before. So there's no significance in that digit. So what this essentially means is that when you add this number to this number, it's not going to change this number. And in fact, not even considering significant figures, it won't change that number. So let's just do the addition here. The first number plus the 1.758 times 10 to the 26th will give you the same number. Essentially, it'll give you 1.4361 times 10 to the 31. And then as a final step, we round that to the correct number of significant figures, which would be 1.44, right? Because there are three significant figures, times 10 to the 31 molecules. So our final comparison here, now we want to know which student emits more CO2 molecules in a given year. And you can really just look at the exponents here because they are such big numbers. The total emissions from student A is on the order of 10 to the 31st. And if we go back to the total emissions, that was student B. If we go back to the total emissions for student A, you've got 10 to the 29. So student B is actually emitting more CO2 molecules each year than student A, because 1.44 times 10 to the 31 is a bigger number than 1.0 times 10 to the 29. And that's it.